some initial issues, but we'll try to start on time starting next lecture. All right, so I hope everybody can see the overhead. Okay, all right. Okay, so last time we were discussing Unix system calls. Right? And we said, okay, firstly, here is the kernel or the OS. I'm going to use this, the OS kernel. And here are these processes, P1, P2, and so on. And these processes are isolated from each other. So they have their own private memory or private address space, right? So private address space. So this is the space where they store all their variables like global variables, local variables, all these variables, even the code, etc. are all stored in this address space. And so the process can just operate on this address space and no other process will ever be ever able to read or write whatever the another process is doing, right? So each of the private address spaces where they store their code and data. And so that's enough for a process to be able to do computation. But if a process wants to do something which involves accessing shared resources, then it makes system calls. So it makes a system call and the OS returns the result. So some of the system calls are, for example, to create a new process. All right, or access a device. All right, or access a file, and so on. Right, so more examples like this. So and reason these things cannot be just the reason a process needs to make system calls to be able to do any of these things is because these things are actually shared, right? A device like a monitor or a keyboard or a mouse is shared device which is shared among multiple processes, and you don't want that one process should completely control a device. So an operating system sits in the middle and it acts as a broker between the process and the resource. In this case, the resource is the device. So, and the process makes a request to the operating system. The operating system internally checks whether the process is authorized to make this request or not, right? So for example, a process should not be able to write to any part of the screen. It can only write to the part of the screen which has its window, for example, right? So, or it should not be able to access any file. It should only be able to access files that that belong to the user which is running that process, right? So it should not be able to access, for example, files that belong to another user or the root user, right? So all these things the operating system will check internally, and so that's why the process needs to first make a call to the operating system to be able to do these things. So because these are all privileged operations. Also, creating a new process requires operating system involvement. The process actually requests the operating system to say, please create a new process. The operating system will internally figure out that whether there is enough memory to create a new process or not, whether this user has already created too many processes, so there's a limit to how many processes it can create, and depending on that, it will either entertain the request or reject the request, right? Okay. All right. Okay. So let's look at the system call. Review the system call that we looked at last time. There was fork, which created a copy of the current process. Exec, which replaced the current process with a new executable. Read, which was used to get input from a particular resource like a device. Write, which is to give output to a particular resource. Exit, which is a system call to say that I want to terminate my current process, right? Finish the current process. Wait, which says I want to wait on one of my child processes, right? By waiting on my child process, I want to wait for it to exit. All right. Okay. And so we saw a program called shell, and we saw how a shell is also a process, right? So a shell is actually executing as a process over the kernel. So it's a program, and it's basically making system calls to execute its functionality. So for example, it makes a system call called write to print a dollar character on screen. Then it makes a system call called read to read the user command, and then it parses the command, and then it calls fork to create a new process, and inside the new process it calls exec to actually execute that command, right? Finally, the new process could potentially call exit, and so the shell actually waits for the new process to exit before it actually displays the next dollar prompt, right? So it was a nice example of how these system calls work, and how a popular program like shell uses these system calls to work. We're going to study today more functionality. So we're going to look at how shell does other things, right? So let's say this is the shell, and another. So I said if you say ls, it basically prints to the console, and then the next command comes, right? So some directory contents, right? And if I say ls greater than foo, file foo is the file name, then it doesn't print anything to this console, but it just prints the contents of the directory to the file foo, right? The contents are not printed on the console, they are printed on the file foo. Right? So how does this work? All right. So let's see. Recall that in the shell we had a system call called write, and we said write 1 comma some buffer in this some string, which is in this case dollar and space, and the size of the string, which is 2 characters, right? So, and we didn't really discuss what this 1 means. I mentioned last time that 1 will point to, let's say, the monitor, the console or whatever. Okay. Now, how does this happen? What? And then we said, okay, we're going to say read 0 and some buffer, buff and some size of the buffer, let's say 100 characters, maximum of 100 characters. The return value of read is basically the number of characters that were read. So when you say n is equal to read 0, buff 100, you're basically saying that read a maximum of 100 characters into buffer buff. But if if the number of characters typed by the user is less than 100, then just return how many characters have been read, and only those many characters are filled into buff. Right? So for example, if 30 characters have been read, then only the n return value will be 30. On the other hand, if no characters have been read, then the return value will be 0. On the other hand, if there was some error in the system call, then the return value could be less than 0, negative. Right? So we said that negative return values usually indicate error conditions. All right. And we said that 0 is taking input from the keyboard. Right? So this is a way of telling the operating system that this is the keyboard. So I'm going to actually generalize this. This is actually not completely true. All right. 1 does not necessarily refer to the console, and 0 doesn't necessarily refer to the keyboard. What happens is that for every process in the system, let's say this is the process P1, and this is the kernel, the OS kernel. With every process, there is an associated table inside the operating system kernel, which is called the file descriptor table. File descriptor table. And what this table contains is basically it's just a table starting from entry 0, 1, 2, and so on. Right? I hope everybody can read this. Okay. So 0, 1, 2. So let me just draw a bigger picture so everybody can read it. So with every process, so let me write per process FD table, right? File descriptor table. And here is what the file descriptor table looks like. It contains entries up to whatever the maximum number of file descriptors you can have. So let's say the maximum number of file descriptors is, let's say, 255. So it'll have 255 entries in this table, and the first entry is 0, 1, 2, 3, and so on. Right? And these point to some resources. So these are pointing. So for example, 0 can point to keyboard, 1 can point to console, and so on. Okay. So when I make a system call called write 1, comma something, I say hello, comma 5. That's, hello is a string of length 5. Then what's happening is that it's writing the string hello to file descriptor number 1, wherever file descriptor number 1 is pointing. So in this example, it was pointing to the console. So when I made the system call called write 1 hello, the string hello gets printed on the console. Okay. On the other hand, if instead of the console, I said, I had pointed it to the serial port, right? What is the serial port? Serial port is another device on the system. So if you have seen your computer, the older computers used to have this slot which had the serial port, and you could connect a wire to the serial port and connect some other kind of device to the serial port. Or let's say, for example, you could connect a printer to something like this, right? Or you could connect something else, some other device which also does similar functionality as a monitor, which is an output device. So there's a serial port or printer or whatever, right? And so if this file descriptor was pointing to another device, not console, then the same command write 1 hello 5 is not going to print hello to the console, is going to print hello to the device, whatever the device. All right. Similarly, the input need not necessarily come from the keyboard, right? The input may be coming from, let's say, some network protocol, right? In which case, if I say read may take input from the keyboard. So when I say read 0 and I say buff and 100, read, depending on where 0 is pointing, the input will be taken from that particular device. If it's keyboard, then the input will be taken from keyboard. If it's a network, then the input will be taken from the network. Okay. So there's a question, what is the actual meaning of kernel in terms of operating system and how it is made? So let's just assume that whatever we have been calling an operating system for now is the kernel, right? So let's say that the kernel basically means this lowest layer of software which sits on the hardware. So far I had been calling it the operating system, but I'm going to also call it the kernel. So the kernel is basically the operating system. Okay, let's just assume that, and we are going to get more and more understanding of what is a kernel versus exactly how it's implemented and all that as we go along the course. But let's just say that the layer that sits at the very bottom on the top of the hardware is the operating system kernel, and I'm going to call, I'm going to use either the word operating system or the word kernel interchangeably. So they both mean the same thing. All right. So this number in the system calls write and read basically is a file descriptor number, FD number, right? And the kernel maintains an FD table per process, and it looks for it searches this table for using this number. It indexes this table using this number, and whatever device is being pointed to by that particular entry, that's the device that it wants to write or read from. Okay, all right. So firstly, how does this table get created, or how does this table get initialized? There is a system called, another system called open, right? And the way open works is you can say open some file name, and in what mode do you want to open it? You know, let's say read write mode, right? You could alternatively say open file name read only mode. Right? This is a read only file open. Alternatively, you could say open some device name, right? So for example, you could say /dev/ hypothetically speaking printer, right? And you can say, oh, it's a write only mode. In the write only mode, you can only write to the printer. You cannot read from the printer. It's an output device. Okay. So what happens when you make the system call? When you make the system call called open, it returns a number, and that number is nothing but the file descriptor, right? Each of these, so an open system call, the return value of the open system call is a file descriptor. And the semantics of open are that the kernel or the operating system is going to, so if this is the FD table, it will go through the FD table starting from the beginning, starting from 0, then 1, then 2, and look at the first available empty slot in this file descriptor table. If there's an empty slot, I basically create a mapping from that empty slot to this particular device. So let's say I did printer, so I'm going to create a mapping from this particular slot to printer, and whatever is the number here, let's say the number here was 3, then the return value will be 3. Okay, so that's how open works. Okay, so question is file descriptor table, does the file descriptor table act as a pointer to the command? Yes, you can say that. I mean, the file descriptor itself is basically saying, you know, which entry in the file descriptor table I want to do this operation on. And so the file descriptor table is basically say, acts as a pointer inside the file descriptor table and says, you know, this is the resource that I want to access. Right? So now, for example, if I say FD is equal to open/dev/printer in write only mode, and let's say the open system call succeeded, then my return value will be 3, assuming, you know, 0, 1, 2 have already been somewhere. So they are already busy, and you know, 3 was vacant, so I got 3 back as an answer. Now if I say write 3, comma some hello and 5 characters, then the string hello will get printed to the printer. Right? On the other hand, if I had actually done, instead of open/dev/printer, if I had done something like open some file name foo, then the next command write 3, comma hello, comma 5 would have written to the file, not to the printer. Okay. So open basically creates a mapping between the file descriptor number and the resource, and then the write system call just basically takes the file descriptor number and prints to that particular resource, whatever it is. It doesn't care. Right? It just says number 3, whoever it is, whether it's a file, it's a printer, I don't care. There's a level of indirection here by the table. Okay. Similarly, I could say read, right? And if I say read 0, 0 could be pointing to the keyboard, 0 could be pointing to a network input, 0 could be pointing to a serial port or any other device which could be an input device, right? Maybe the mouse or something. So these are all possibilities. Okay. All right. So that's okay. Now let's see what happens. What happens on a fork, right? So let's say this is a process P1, and here is P1's FD table. Let's call them FDs. P1's FDs, right? Now this process called a fork, right? So what happens is another clone process gets created, P2. But also the entire FD table gets copied, right? So P2's FD table gets created. These are P2's FDs. Except that all the entries in P2 FDs are identical to all the entries in P1's FDs, right? So if if this was, let's say, pointing here, then this one will, let the 0th entry was pointing to a resource called foo, then the 0th entry of P2 will also point to foo, right? Let's say the first entry was pointing to something called bar, then the first entry in this will also point to bar. Okay. So when you call fork, so this was basically created through fork. The file descriptor table itself gets copied. Can I have another pen? All right. So let's see what happens when the shell executes. All right. So let's say the shell was executing. This is the shell, and here is shell's FD table. Let us say I was executing the shell program on the console and the keyboard, right? So in this case, 0 will probably keyboard, and 1 will point to console. Right? In another scenario, the same program without any change in code. Let's say here's another example. I'm executing it on the OS, and once again it has an FD table. But in this case, 0 may be pointing to network or even a file. You can take input from a file, and 1 could be pointing to another file, right? If you do this, the shell program itself doesn't change. It's the exact same program. You're still making system calls which say write to file descriptor $1 and something, right? And then you're making the system call called read on 0 buff. Right? Except that this time when it writes something, it's going to write to the file. That's a file output. And when it reads something, it's going to read from, let's say 0 was pointing to the file, then it's going to read from the file. What you can do is you can actually, instead of making commands from the keyboard, this file could be actually a script called .h, and this file could contain multiple commands, one after another, separated by the new line character, right? So for example, if file.sh says ls and then let's say cat hello, right? or echo hello. Echo is a utility which just prints whatever you are typing as an argument to the standard output. So what happens is that this file gets executed as a shell script. Right? The program is the same. You just change its environment. Right? This FD table is the environment of this program. You just change the environment such that the input will now be not be taken by the keyboard, but will be taken from a shell script, from a script which has a sequence of commands. So when you execute this shell in this new environment, it acts like an execution of a shell script. All right. As opposed to the previous case when it was actually taking input from the keyboard, this time it will start taking input from the file and parse each command one by one and execute it one by one. Right? So this is a nice composable way. So it sort of allows you to separate the program logic. So this contains the logic, which just assumes that I'm going to write to file descriptor 1 and 0 from the environment of the program. So this is the environment. Right? You could run the same program logic in different environments to get different functionalities. Either I could have a shell on which a user can type, or I can change the environment to have the same program behave like execution of a shell script. Right? Okay. So let's come back to our old example. The shell is running in this environment where 0 is pointing to keyboard and 1 is pointing to console. Now let's say the user types the command ls. Right? What happens is a new process gets created and the executable for ls gets loaded into this process, but also the environment gets copied as it is. Right? So this table gets copied, and once again 0 is pointing to the keyboard and 1 is pointing to the console. The program ls does what? It reads the contents of the current directory and prints them to inside the ls. It's probably doing write 1 comma something, some buffer, what the contents are. So ls itself is going to write to a file descriptor number 1, irrespective of where 1 points, right? So when you executed ls is not going to execute any open or anything of that sort. Ls is just going to say write this particular buffer which will contain the directory contents to file descriptor 1. How did the file descriptor 1 get initialized? It got initialized by the shell. If the shell was executing on the console, then ls will also print to the console. If the shell was executing on the serial port or the printer, then ls will also print on the printer. Right? So that way the environment of the parent process, which is gets transferred to the environment of the child process, which is ls. And so ls also needs to be completely unaware of where it is executing. It just says I want to write to file descriptor number 1. Okay, there's a question. Is FD table predefined for an OS or user can change it according to his own purpose? So yes, the user can change it according to his own purpose, but it can only change it using open system calls, right? Also, we're going to look at more system calls later, which allow you to change it. But the only way to change the FD table is through system calls. A user cannot directly change or access the FD table. It can only manipulate the entries of the FD table using system calls. Right? Why cannot a user program directly access the FD table? Why doesn't an OS allow user to directly access the FD table? For security, right? Because the FD table is pointing to shared resources like keyboard, console, and all that. And so the operating system needs to ensure that the FD table is always pointing to resources that are accessible to this particular process, right? For example, some devices may not be accessible to this particular process, or some devices may be shared. So the operating system needs to make sure that all accesses to multiple concurrent accesses by multiple processes to the same resource are appropriately getting handled. Okay. Another question: are 0, 1, and 2 default descriptors, how we can change them to our own resources? Okay, very good question. So far I've been saying that the programs are written such that they say write 1 comma something or read 0 comma something. So these are actually special 0, 1 and 2 are special file descriptors. All right. So the file descriptor number 0, so let's say these are FDs, file descriptors. File descriptor number 0 is called standard input, STDIN, standard input. File descriptor number 1 is called standard output. Right. So basically the meaning of the shell program is that it reads a command from the standard input and prints the value output to the prints the $sign on the standard output. Also, the standard output gets copied from the shell process to the parent process to the child process, right? There is another and the child process itself is going to probably write to its standard output or read from its standard input, but because the standard input and standard output of the child process are identical to those of the shell process, the same program can run in different environments, and depending on where the shell was running, the child process will run in exactly the same environment. All right. Also, there's another file descriptor called 2, which basically is called the standard error file descriptor, std error, and this is used to distinguish between a normal program output and a program output which indicates an error condition, right? So you could say that standard output needs to go on the console and standard error needs to go to the printer, right? For example, you don't care about standard output. You say, okay, standard normal output I don't care about, but please I need to know urgently about anything which is an error condition. So you could say, okay, let me redirect standard error to some network device. So it's going to, let's say, send an alert to my mobile phone, and standard output is going to still output to the console, right? So that way there is a division between what's a standard output and what's an error condition. Okay. So for example, a program could say 0 goes to keyboard, 1 goes to console, 2 goes to file, right? And so on, or network or whatever. Okay. Okay. So the last 15 minutes left. It's a short lecture today. I'll take questions at this point if there are any. VIT JPR. I cannot hear you. VIT JPR. Cannot hear you. Okay.
Hello, sir.
Hello. Yeah, I can hear you now. Yes.
Hello, sir.
Hello. Yes, VIT JPR,
Yes,
please. Yes, I can hear you.
sir,
Hello.
my question is that suppose if we are writing any command in the console or in the command prompt or terminal, and if the hello, sir.
Yes, yes, I'm hearing you. Please continue.
Hello. Yes, sir. Sir, if you are writing any command in the terminal or command prompt in Linux or in Windows, suppose if we are executing any command. Suppose if you are writing any command and that command is incorrect. So a dialog box appear representing that this command was incorrect. So how could it detect that the command was incorrect and the proper dialog box for that incorrect command is shown at the output or in terminal? That's my question, sir.
Okay, I think we had taken this question last time also. Question is, if there's an incorrect command on the shell, then how is it handled? Well, let's say this is the shell, and okay, so let's say I type a command called ABC, right? So what happens is the shell searches for this file called ABC in its path variable. Right? There's an environment variable called path. Let's say the path variable is initialized to /bin. So it searches for this file called abc in /bin. So let's say /bin/abc. If there is no such file, it basically says, I'm not going to fork any other process, and just prints to its third output or standard error that the command failed. Okay. There was another question. What is the size of the FD table? Is there a maximum size? Right? FD table size. So yes, the size of the FD table is is constant. On Unix, I believe it's I think 255 maximum. In general, you would want that the first three file descriptors 0, 1 and 2 are always initialized. Others may not be initialized. All right. It's also possible that a process is executing with a completely empty file descriptor table. That's also possible. Right? In which case it will not be able to do any input output to any device or file descriptor table. Okay. Question from SMIT. I cannot, huh? Please ask the question. SMIT? Please ask the question. SMIT?
Hello, sir.
Yes, please go ahead.
I have a question. So, how do we change the file descriptor values?
Yes, please go ahead. How do you change the file descriptor?
The file descriptor value 0 is pointing to file.sh.
How do you change the file descriptor? Okay, good question. Very good question. How do you change the file descriptor values? So let's say here's a process, and here is the file descriptor. Let's say this is shell, and 0 is pointing to keyboard. I want to change the value, right? I want to make it point to something else. I cannot directly go and change the file descriptor because I cannot access the file descriptor table directly. But what I can do is I can first, so there's another system called close. This is what I wanted to do, but didn't have time, but let's discuss it now. So I could say close on 0. Right? It basically means that whatever it is pointing to gets removed. Right? So this entry becomes uninitialized. And then if I say open, let's say I wanted to open a file. Right? Let's say I wanted to open a file foo in read mode. Then what happens is the operating system will search for the first available empty entry, vacant entry. In this case, the first available vacant entry is 0 because you just close 0, so it's now vacant. And so what will happen is now this will point to foo. Right? So you can change the value of a file descriptor entry by first closing it, closing the current value, and then opening a new value. Okay, assuming that all other file descriptors are full. So let's say I wanted to change the file descriptor value of file descriptor number 15, right? And let's say 15 is pointing somewhere. Right? Let's say it's pointing to foo, and I want to now change it to bar. So if I say close 15, right? And then I say open bar, then the Unix kernel will start from 0 and look for the first available vacant entry. If the first available vacant entry is less than 15, then the return value will be whatever that value was. Let's say it was 10, then it will return 10. If on the other hand 0 through 14 are all full, then it will return 15. Right? It doesn't really matter what the value of the file descriptor is, right? It just what matters is that you should be able to access, you should know what the value is for the resource that you open, and then you use that value to access it. The only values that actually matter are 0, 1 and 2, right? Because 0 has a special meaning of standard input, 1 has a special meaning of standard output, and 2 has a special meaning of standard error. And so I initialize them. If I want to change, let's say, my standard input, what do? I close the current standard input and open a new resource, so that standard input will get replaced. Similarly, if I want to change standard output, I could say close 1